We are very happy to invite Mohamed to attend our SLS talk. Let me first make a brief introduction about our SLS talk platform. SLS talk is an event to provide a platform to sharing the research work conducted by graduate students and learn research ideas from peers. And the title of the presentation will basically, the topics that are mainly conducted by our SCSE labs. And also participants in this event as a speaker can earn 2 GAP hours. If you have interested in SLS talk, you do not hesitate to send your email to us. And we will also thank you to advertise our SLS talk. Then let me introduce Mohamed. Mohamed is a first-year PhD student at NTU. His research interests include deep learning, transfer learning, and intelligent fault diagnosis and prognosis. In this talk, he will present a novel adversary multiple target domain adaptation method for single source multiple target problem, where the model can generalize to multiple target domains concurrently. Now, welcome Mohamed to start his talk. Mohamed, are you ready?
Yes.
Okay.
Can you see my screen?
Okay, yeah, I can see your screen.
Yeah, just for correction, actually, I'm a fourth-year PhD student.
Yeah.
Yeah, so good afternoon, everyone. This is Mohamed Ragab with you, and thanks for your time for attending this talk. Yeah, today I will be talking actually about, a bit applied topic of predictive maintenance and how our work have been able to address some of the problems in this predictive maintenance application. Okay, yeah, a biography, as John mentioned, thanks to him. Actually, I have joined, NTU since 2018, August. Before that time, I have done my master's and my bachelor's in electrical engineering in Egypt. Currently, I'm doing my PhD with NTU, but concurrently, I'm also a research scholar with ASTAR, Institute of Quantum Research. And these are some of our publications. Today, for the time limitation, I will only introduce one work, and I will talk more time about this. Okay, for our outline today, I will give a bit more focus for the background, because I believe that none of you have some background about this application and some of the challenges, and I will show one of our solutions and how we address these problems. And that's it for our talk. Our work actually is in our daily life. We rely on a wide range of industrial machines. You can have in aircraft, you have rotating industrial machines, in trains, in ships. In everyday life, we have such a machine. But actually, every machine is going to fail until it's being properly maintained. So maintenance actually is, a mandatory task and a crucial task to increase the machine usability. Okay, how to do maintenance? This is another question. Actually, there are three, famous maintenance strategies. The first strategy called reactive maintenance. Actually, this is quite simple, where you replace the failed or the damaged components after its failure. And this is okay, if you can adopt this approach if you are working with simple machines or simple components like light bulb or something like this. But actually, with very complex and in quite real industrial machines like turbofan engines, for example, or something like this, this can be extremely costly and affect the safety. Actually, you cannot afford, failing of such approaches. So another approach has been adopted is actually, rather than just waiting for the failure then replace the damaged components, preventive maintenance is the most famous one so far. Preventive maintenance mainly actually aim to do regular maintenance for the machines to prevent it from failing. However, actually, to do so, you need to be a bit conservative. For example, you cannot wait for the machine to fail. You need to make it a bit earlier than the machine failure. So you usually make in a bit conservative way. So you have large downtime. Each time you do maintenance, you actually you shut down your factory and then you apply your maintenance. But this actually can be extremely costly. because imagine like for some manufacturing industries, you know, downtime for 1 hour could reach to $2 million. This is too much, and actually it's quite costly if you are every time you do maintenance, you remove some failing parts and then do this, increase the downtime. This is not only the problem. The problem is that you can remove some parts that are still usable because you are not maintaining based on the machine condition. You are just maintaining based on a pre-scheduled appointment. So the main question actually we need to know is when exactly we do maintenance. And this is what actually predictive maintenance is doing. Predictive maintenance actually is trying to do this scheduling based on the machine condition, and schedule the maintenance just before the fail. By predicting exactly when the machine will fail, I just can schedule my maintenance just before the failure. By this way, I can use my machine until its end of life, then I save money. And I'm also reduce the downtime because I don't do regular maintenance. I just do maintenance based on when the machine is going to fail. But and this can actually, estimating now, people start to apply this, you can save roughly 8 to 12% over preventive maintenance. However, actually, knowing exactly when the machine will fail is a quite long-standing problem. Okay, let's go through some of the process that we usually do to apply for predictive maintenance. Usually given some data and multiple sensors applied to, for example, this is a turbofan engine. And, these are the sensor readings that we have. The first step is we usually do like data cleaning and pre-processing. And actually, this is a quite underestimated task that can be time consuming and significantly important to the performance. So we usually do normalization, remove, because usually sensors are not, perfect. Some sensors may fail at some times. You need to remove failure points of the sensors. So this is like data pre-processing is a very important step. So after, you can see before cleaning and after cleaning, the pattern could be a bit more clear. Then we have like something like condition indicators. This is one way. Is that given these kind of signals, we try to identify a condition indicator. For example, here's like a frequency spectrum, and I can see that there are some type of faults that can, have high peak at this low frequencies, and other type of faults can have, high peak at this high frequencies. So they are separate, separate effect based on, the source of fault. By leveraging these condition indicators, we reached our end tasks where we do anomaly detection first, whether like there is a fault already happened in the machine or not. After we assume that we have a fault, we need to classify what type of faults. We need to detect where exactly the failure part is. And actually another, which is the most important one, is the remaining useful life estimation. Where given the current machine condition that has not failed yet, you need to estimate when exactly the machine will fail. And this we call the remaining useful life. In this talk, actually, we will focus on one task. We will talk about fault classification, just for the time limitation. If we have time, we may introduce this remaining useful life estimation. Okay, finally, after you already developed your model, you can deploy your model on the edge device or on the cloud. This is like a summary of the predictive maintenance workflow. Okay, then how to develop such models? As we mentioned, I mentioned about a model. Actually, models can be either physics-based model, where experts try to mathematically model the deterioration process of the machine, and based on this mathematical modeling, I can try to do my own task, either anomaly detection or fault classification, or even remaining useful life estimation. However, recently, there is evolving complexity of the industrial machines, and actually, physics-based approaches are no longer easily attainable because it's becoming very, very complex, and even experts cannot easily model this. At the same time, with the big data era, lots of data from these manufacturing industries are available. So leveraging this data, we can actually, leverage data-driven approaches and the advances in data-driven approaches and this availability of data to improve the performance. Two main approaches has been followed in this application. One main, which is a conventional machine health monitoring approach by using conventional machine learning, by manually extracting hand designing features for each class or for each task, and then use some conventional techniques like LDA or PCA, and then apply your classifier like neural network or support vector machine. However, these kind of conventional machine learning approaches can be time consuming and not robust, because you need to manually design each feature for each class, and not scalable actually. Recently, we know that we have large availability of data. People have leveraged deep learning to automatically extract features rather than relying on domain experts. You can automatically extract features with the availability of data. However, actually, deep learning now is achieving state-of-the-art performance, but it's actually mainly work under two main assumptions. First, that training data and testing data are like sampled from the same distribution. And second, that especially for deep learning, the most successful paradigm is supervised learning so far. And it's mainly rely on the availability of vast amount of labeled data. But in realistic real-world manufacturing industry, are these assumptions practical, or can we deploy such models with these limitations? Okay, let's see. Assume like you are dividing, or same machine, for example, are already deployed in two different places all over the world. This machine actually is already like working under different working conditions in case temperature, pressure, lots of things. If your model has been trained on this condition, will it be able to work well on another condition? This is a problem. Even inside the same machine, you could train your model on one part of the machine. But if you are trying to testing your model in another part, this also could be challenging. Also, assume that I have no data for this machine, but I have data for related machine. If I want to test my model for this machine, can I rely on related machines? Will it work? Actually, this is a well-known problem called domain shift problem, where the training and testing are different, and because of this, even your model that has worked very well for the source working condition or the source location can fail to generalize well on the target, because the variability of the distribution of the data. We need to address this problem. Actually, we aim to address this domain shift problem, either between machines or between locations, but at the same time, we also need to assume that we don't have labels for our target machines. Why? Because for some machines, actually, labels are failures. So when the machine fails, this is a labeling like what type of failures that have happened. So some machines take up to years actually to fail. So waiting such a long time to get some labels, this is unpractical. And second, even some machines are not allowed to go to fail. A turbofan engine of an aircraft, you cannot allow this to fail while it's working. So, which is a catastrophic problem. So because of these issues, we usually a scarce label problem is an issue. So to address this issue, we first, propose our first work, which is, adversarial multiple target domain adaptation for fault diagnosis. I will talk about preliminaries first. We actually leverage domain adaptation track, which is a sub track of transfer learning, but mainly try to address similar problems. So actually, I will not try to be complex, but the key idea of domain adaptation here actually is that your empirical risk on the target domain is bounded by the empirical risk on your source domain, and the discrepancy or the differences between your source distribution and your target distribution. And these factors actually related to the conventional VC dimension of conventional machine learning. So the key idea here actually, if you want to bound or you want to reduce the target risk, you need to reduce the source risk first, which is our source machine. This can be simulated data or publicly available data that we have, and also reduce the discrepancy between the distribution of the source domain and target. So the key two tasks I am aiming to do is first minimize the source risk, which is minimize the performance on the data that I already have, and then try to minimize the distribution between the source data or the source task and the target data. By doing these two tasks, I can improve the performance on the target data. Visually, you can see here that I have a source domain and target domain, and assuming they are spanning the same type of classes, but you can see the classifiers that work well for source domain cannot generalize well for the target domain, as the class distribution is different. So what we aim to do first is to produce domain invariant features, such as that whatever the domain, the features has to be similar. Then you need to have a class discriminative features, that each class is separated from different classes. So by this way, classifiers that works well on the source will work well on the target. This is the key idea of domain adaptation in general. Okay. In my applications, there has been lots of work that has been, tried to address this problem by leveraging domain adaptation, either by using some statistical distances or domain confusion losses or whatever. However, actually, the key problem for these approaches is the scalability. To clarify, in domain adaptation, usually it's work with something called single source, single target. So you have a single machine, a source machine, and target machine. If you change your target machine, you need to retrain a new model independently from scratch. Or even your source model has changed, you need to train a new model independently from scratch. So this is somehow not scalable because I can have multiple working conditions at the same time. So for each time I retrain a new model, even if I can generalize well with domain adaptation, but the problem of retraining a new model is not a scalable solution actually. Because for k working condition you need to have this kind of number of models. So in this work, we aim to address this kind of limited scalability problem of distinct approaches. And also we assume we have varying working conditions, and also we have unlabeled target data. Yeah, so we devised a new approach called single source multiple target domain adaptation. We leverage adversarial domain adaptation with multi-class classification. Okay, yeah, this is our architecture. So the key idea, actually, we first pre-train our model on the source data, we're assuming it's labeled. And then we have like a multi-target domain data, and we have like a domain discriminator. And the key idea actually is to train these 3 target models to produce domain invariant features such that all the features of all target domains can be invariant from the source domain. After doing such scenario, then we either pass any of our target domains, our target mapping, which is domain mapping here, can map this target to, a new feature representation that is similar to the source. And now the source classifier that works well on the source data can work well on the new adapted representation of the target data. Okay, this is like the algorithm. We have like 3 main losses, or 2 main losses actually. There's a cross entropy loss. This is normal for the source pre-training, and the adversarial multiple target domain loss, where try to train multiple feature extractor against the discriminator. And this is the algorithm. Actually, to clarify it in a visual way, I prefer usually visual, abstract. I tried here to emulate what's happening in our approach in a simple way. So given our source machine, which is assuming that we have availability of data for this machine, initially the features are not classified already. So we use our source, simple cross entropy loss and classifier and our source feature extractor to obtain class discriminative features. Okay, given that we have no labeled data for our target machine, the best we can do is we leverage this source pre-trained model by sharing the weights of this model to this new target models, and pass our target data or target to our model, which is pre-trained with the source model, and try to classify. However, initially, the source classifier that already worked well for the source data cannot generalize well actually for the target data, because as I mentioned, the distribution shift, they are different machines or different working conditions. So here we leverage our approach actually of this adversarial alignment. The discriminator will try to push the target feature extractor to produce domain invariant features, such that the features of the target and source are no longer distinguishable. By this way, the classifier that works well on this feature representation can work well on this new representation of the target data. And here in our testing, we can directly feed any of our target domain data, and our model can work very well. This is like the approach. Let's see the results. Okay, to test our model, actually, we have leveraged 2 test scenarios or 2 case studies. Our first case study is a data set generated by Case Western Reserve University. This data has been collected under 12 case samples per second for bearing data set, rotating machinery, and under 4 different loading conditions. So this machine has different loadings, and each loading condition will be considered a domain. And for each domain, we have 10 total fault classes. And the signal for each class actually was this sample length. So first, to see how our performance, we usually do a transfer improvement test, where we directly test our source model on the target data first, and then we test our adapted model on the target data. what you can see here is actually our adapted model can improve the performance significantly over, the source model, which is without adaptation. We have like, we could reach at some scenarios, these are different working conditions, but at some scenarios, we could reach improvement over 11% accuracy. And on average, we are achieving 6% improvement. Also comparing with some baseline methods, we already outperformed these baseline methods. Although these baseline methods actually were single source, single target, but our approach is single source, multiple target. So to clarify, as you can see here, all existing domain adaptation approaches, usually you need to train a new model for each cross-domain scenario, as you can see. So for this experiments, I may need 12 models. But in our approach, actually, we can generalize to multiple target domain concurrently, given the same source domain. So here, like this is one model, this is a second model. So we only have 4 models compared to 12 models for the, for the existing approaches. And at the same time, actually, we are outperforming these approaches in all of them. Okay, to further evaluate the efficacy of our approach, we also use a quite, famous, testing datasets called, generated by Paderborn University in Germany. And this data has 4 different operating conditions also, but here the operating conditions are resulting from different key parameters, like rotational speed of the motors are different, loading torque of the motors are different, radial force that applied on the motors are different. So this is also the performance. You can see for some working conditions, the performance is already same because actually changing some parameters here does not significantly affect the performance, but changing other parameters can be detrimental to the performance. So you see, like for some working conditions, the source and target are almost achieve very good performance because there is no domain gap between these two. So source model can work very well on the target model, but there are actually some scenarios where the source model can fail to achieve very good performance, as you can see here. So in our approach, actually, as we can see, there is we achieve significant improvement over certain methods here. However, our approach actually is not problemless, because as we mentioned, we are generalizing to multiple target domain concurrently. So if the domain gap between different domains is not consistent, I mean, some domains have very large domain gap, other domains have very small domain gap, this can harm our performance. You can see here, we are not achieving the best on these 3 scenarios when, mapping to domain E or this, this. So this, we are not the best in these 2 scenarios. So actually, this is a case where, because we're aiming to achieve everything, which is cannot be, you need, like, there is no free lunch theorem. We already improve the scalability of our model and achieve very good performance. But at some times, when the domain gap is not consistent, you may not achieve the optimal performance. Okay. Also, our code is publicly available in GitHub. Thank you so much.
Oh, okay. So now, if you have, if the audience has have some questions, you can send your question in the chat box. And now, the QA session. I have a small question first.
Yes.
Okay. Yeah. You utilize the deep learning to make the fault prediction. So, as a deep learning user, I want to know which attribute of input will play an important role in your prediction. So, is it possible to support such function?
You mean, for example, which attributes in the input are quite relevant to the classification task?
Yeah.
Okay, this is a very good question, actually. But so far, initially, as we know, we leverage deep learning based on some objectives, which is our losses that we have. But there is no clear attributes because we usually input the raw input data, the time series as I have shown to you here. Yeah, we input the raw input data directly to the deep learning model. There is no task of feature extraction or feature, attributes.
Okay.
We usually apply directly on the input data.
Okay. A further question.
Yes.
If I based on my personal understanding, your domain is the number of your domain is fixed. If I have another new domain, for example, I move from Singapore to USA, or move from and if I want to add Canada or Korea, and for the model trained for Singapore and USA, we need to retrain that.
Yes, but the key idea here actually, domain adaptation is addressing, or our approach is addressing so far, is that you don't need to have labels for your USA model, for example. And this is the key problem for our application is the labels. So we can generalize or relying on our Singapore model to improve the performance on USA model without needing any label data, which is quite strong assumption, but quite practical for our approach. Because labeling an image is quite simple, but labeling time series data is significantly harder.
Okay. So for audience, don't be shy, and you can send your questions in the chat box. It's a great opportunity to. Okay. We have a question from Terence. The classify and discriminator loss is clear, but can you explain the feature extractor loss again?
Okay, so let me go to the losses. Okay, yeah, here actually this is like the adversarial loss. So here the discriminator loss first actually is trained, to identify well each data of the source and target domain, distinguish or classify between the source data and the target data. However, our feature extractor actually is trained to do the opposite. It's actually trained to confuse the discriminator loss. So here our loss is actually because we have multiple shared target domains. These are actually trained against this discriminator, such that the discriminator loss will be maximum. So in other words, our domain discriminator is trained to minimize this LD loss, but our feature extractor is trained to minimize this E loss, which is maximizing this LD loss. So we try to confuse this discriminator loss.
Okay. Terence got it. Okay, so for other audience, if you have a further question, you can ask directly in the chat box now. I have a small question now.
Yes.
Whether the adversarial idea is a key technique to address the limited data labeling.
Okay, because the key idea here is that to align these two domains, I don't need any label. Because what I do here, I just need to label what's data from source and what data from target, but I don't need to have access to the class label. I just add labels to these domains, which is quite easy. This is the Singapore model, this is USA model. Just, for example, put label of 1 to Singapore model, label of 0 to USA model. This is a quite simple task, and adversarial network can work with this. No need to know the class label.
Great. Okay. Okay, Terence has a further question.
Yeah, this is a very interesting question. I have seen the question that does the final model work well on unseen machine, or do we need to retrain? And actually, we have one ongoing work already. This is already submitted. So the key problem of domain adaptation usually is you assume access to your unlabeled data from your machine. For example, I have Singapore model. I need to have data from USA model, but unlabeled, but I need to have data. But assume I want to generalize to Europe model, that I don't have any data. How can I implement my model such as it can generalize to new unseen Europe data? This is called domain generalization problem, not domain adaptation. And we have already already developed some work. I think I will upload it soon. I will publish it soon. So I will make it public so if anyone is interested. But this is actually quite interesting problem that we have addressed. Is that if you have a new unseen machine that you have no prior data, domain adaptation cannot work well. But domain generalization can work. Thanks for the question.
Okay. So for our audience, do you have any questions? Okay. Mohamed, can you discuss your future work about based on this work? Yeah.
Okay.
Maybe.
Yeah. I still asked this question. Domain generalization, as I mentioned, was one of my future work. Is to generalize to new unseen machines. Because now I am assuming the availability of XT1, XT2, XT3. Although I don't assume I have no labels, but I am assuming I have the data itself. Because to measure this statistical difference, you need to have data. But what if you have XT4 that you haven't seen before, as I mentioned? This is one ongoing problem for my future work. This is one. Actually, another future work I have is, so far also domain adaptation, as I mentioned, assumes that we have same type of classes. The source and target have sharing the label. We said it's sharing like the label space, same label space. But what if we have, for example, USA model has encountered new classes that I haven't seen in Singapore model? How can I do this? This is called domain adaptation under category shift. I'm also have one ongoing work on this area. These are some of the, because by the way, another thing, this is like for fault classification task. I also have some work for remaining useful life estimation task. This is like the remaining useful life estimation task. Usually it's applied for turbofan engines where, given the data at current condition, I need to predict exactly when the machine will fail. This is a failure point that didn't happen before. And we usually rely on this, history, because we have, multiple historical engines that already failed for old aircrafts. So we can rely on this historical data, and we then just try to measure the similarity between our curve here and this historical curve, and try to select the most relevant curve and predict the corresponding failure point. This is a remaining useful life task. So this is another task we are doing already, which is not classification anymore, it's regression.
Okay, so we have two more questions.
Yes.
One is from Terrace. What if the new machine has different input, like different frequency?
Yes, this is always the case. That's why I mean domain adaptation is a player here, because covariate shift is called it's usually called covariate shift bias. So the key idea usually directly testing your model on from historical to the new will not work. So here we rely on domain adaptation. But the key idea is simple. The key idea actually is, when I test directly, it not work. So I do what? I measure like a statistical distribution of each source and target, and try to minimize these differences between the distributions of the historical data and the new data. So at the same time, I apply my normal Poisson true loss, for example, or my normal mean square error loss. So by this way, I can improve the performance of the target domain without needing for additional labels. So this is the way, like minimizing statistical distance on the feature space. This is a key step, because usually people assume on the input space, I cannot change the input data, but I train my feature extractor to do this task for me, to produce a feature that has small statistical difference to the historical data. I hope I addressed your question.
And another question from Sada, how to overcome data set bias in historical data?
Yes, this is called, as I mentioned, the covariate bias or dataset bias, which is the distribution is different. So I think I have just addressed this question.
Okay, so you
unless it's not clear, I think you can still ask.
Yeah. Okay. So for the audience, do you have more questions? You can send your chat box, or you can send your question in chat box. And for the audience, if you have interest in SLS talk, and you also have some publications recently, you can send your email, and we welcome the new participants to attend the SLS talk. Okay. It seems that no one has questions. So we have recorded this SLS talk, and we will send you send the audience of the recorded video to further watch. And now, thank you, Mohamed. And
thank you so much.
Okay.
Thank you so much for inviting me, and thanks for everyone for attending the session.
And okay. If you have interest in Mohamed talk, or
Yeah,
more kind of
you can
research
reach
work.
out to me. Actually, this is my email.
Yeah, you can send your question to Mohamed email directly. Okay. Now we will end our talk now.
Thank you so
Goodbye.
much. Bye bye.